Your last video this year is I'm going to go through some problems. Hopefully that'll help you for your semester test. Okay, we started out with concentration. So we're going to make a molar solution. Remember, moles divided by liters. But in this case, we're going to go backwards because we know the concentration, we know the volume. So if we take molarity times volume, and remember we have to change milliliters to liters by moving it over 3, then we'll get moles. So if I take 3.6 times 0.65 liters, I get 2.34 moles of calcium hydroxide. Now remember, we have to change that to grams because we don't have mole meters. So if you take 2.34 moles of calcium hydroxide, the formula mass of calcium hydroxide is 74. That's 1 calcium, 2 oxygen, 2 hydrogen. And so I get 178.16. So if I measure out 178.16 grams of calcium hydroxide and I add it to 200 or 650 milliliters of water and mix it up good, its concentration is going to be 3.6 molar. Okay. If I add 45 grams to lithium chloride and we have 490 grams of water, what will be the new freezing point? Remember colligative properties? First we have to find molality, and then we multiply it. So I'm going to take my 45 grams of lithium chloride and divide by its formula mass, which is 42.5. So now I got my moles. And then I divide by my kilograms, because again, 490 grams is 0.49 kilograms. So far I found my molality. Okay, now remember, change in temperature for freezing is molality times I, which is the number of ions, the number of particles, times a constant for freezing, which is negative 1.86. This number never changes. I, for lithium chloride, there's 1 lithium and 1 chlorine, so it's a 2. So now I just plug in my numbers, 2.16 times 2 times negative 1.86. And now instead of freezing at 0, it has to be negative 8.04. So it lowered the freezing point that much. Okay, that's colligative properties. Okay, osmotic pressure is another colligative property. When you're doing that, remember, there's a formula. And it looks like pi, but that's osmotic pressure, is molarity times the gas constant times the temperature in Kelvin times the number of particles. So first thing I'm going to do is find M, molarity. It says I have moles, 3.5, and my volume, 400 milliliters, 0.4 liters. So I get 8.75 for my molarity. That's a pretty strong solution. I already know the temperature, 85, just add 273 to it. The number of particles, there's 2 sodium, 1 oxygen, that would be 3. So I have everything I need. I take my molarity, I just found, times gas constant, 0.0821, times my temperature. Again, I take 85 plus 273, and then there's 3 particles, so then I get my answer. So the osmotic pressure needed for this is 771 atmospheres. Okay, that'd be a lot. Okay, here's another one for vapor pressure. Vapor pressure, you have to use your moles of your solvent over your moles of your solution. Okay, so the first thing I usually have to do is they give me my moles of my solute and the moles of my solvent, in this case magnesium oxide and water. So first I'm going to find the moles of them. Moles of water, it says I have 1600 grams. Divided by 18, that's the formula mass of water, 2 hydrogen, 1 oxygen. You get 88.89 moles. And then my moles of my solute, I take my 78 grams divided by the mass of magnesium oxide, which is 40, and I get 1.95 moles. Now, this is what some of you guys do. You take 1.95 divided by 88.89. That's not what you do. You take your moles of your solvent, 88.89, and then you add these two numbers together to get the moles of your solution. Okay, so you take your moles of your solvent divided by the moles of your solution. So you have to add these two, and you get 0.9785. Now you're going to take your original vapor pressure, 23.76, and multiply by that number. Okay, so it's going to lower the vapor pressure from 23.76 to 23.25. Okay, so again, the thing that people do most often is they take this number divided by this number. That's not the case. It's the moles of your solvent divided by the moles of your solution. Okay, we have an equation. We're supposed to calculate the activation energy. Again, when you guys are doing this, all you have to do is set it up. The activation energy is kind of a complicated one to solve, so all you have to do for me is this part. Okay, it's the inverse of the case of the first one divided by the constant for the second one times 8.314 is a constant, and then it's the temperature, the inverse of the second temperature minus the inverse of the first. This is all you would have to do if you're finding activation energy. Okay, you don't have to actually solve it because it gets pretty complicated. I did solve it. You won't have to do that. Okay, solve the following using, okay, so here we have an equation and we have a chart, and what we're supposed to be doing is finding the reaction orders. Okay, so if you look, A changes, we got a place where A changes but B doesn't. Well, A 0.6, 0.2, okay, and 0.15, 0.15, so it's the same. So we're going to have to use trial 1 and 2. And if you look at the difference, you can take 0.6 divided by 0.2 is 0.3, and then divide these two. Well, this one's 3, and this one is 9, the difference between them. So that's why the reaction is 2, because 3, the square root of 3 is 9. So that's your difference. And for B, let's see. Again, we've got to pick where A doesn't change, but B does. And here it does, 0.6 to 0.15. And again, you can divide those. And the difference between this and the difference between this are the same. And again, just take 0.6 divided by 0.15. And you find out when you divide these, you get the same number as well. So that's why you react B. So if it's the same change, it's a 1. If it's the square root of it, it's 2. And if it doesn't change at all, it's 0. And that's all we did, you guys. We didn't do, you can have 3 and you can have 4 and you can have 5. We didn't do those. All we did was 0, 1, and 2. Okay, so the initial rate, so I can pick any of these. I'll do number 3. And it would be A, the concentration of A, to whatever coefficient. In this case, it would be, it's reaction order, excuse me, which would be 2. And the reaction order B would be 1. So you fill in the numbers. 7.0 times 10 to the negative 4th. A is 0.2 to the second, because that's its number, its reaction order. And then B is 0.15, and it's to the first power. And then you just solve. Okay, that's how you do reaction orders. pH, okay, if I'm trying to find the pH, and this is the OH, what I'm going to have to do is take the log of this number. The log of this is negative 8.28, and you lose the negative, but this is the OH. So to get the pH, I'm going to go 14 minus the number I just found, and then I would get my pH being 5.72. So you got to be careful when you do pH and POH, which one you're looking at. Okay, if I have the OH concentration, that's my POH. So if I need to find the pH, take the log of this number and then subtract it from 14. Okay, and again, those are just problems you got to look at carefully. Okay, how many milliliters? This is a titration. 1.25 molar barium hydroxide are needed to neutralize 150 milliliters of 0.69 molar hydrochloric acid. So this is my acid, and I know 2 things about my acid. So I take my 0.69, my concentration, and I got to change this volume to liters. So that's how many moles of HCl. Then I got to write a balanced equation. Acid and a base. Acid I know is because hydrogen is listed first, base because hydroxide is second. Okay, when I get over here, I have water and whatever's left over. Well, barium and chlorine, because the H and the OH make water. Okay, and I got to write the proper formula. Well, I know barium's charge is +2 because there's a 2 over here. And I know chlorine must be 1 because there's nothing here. So that's why I put the 2 there, and then I balance my equation. The reason I need a balanced equation, I got to find my moles. So I take my 0.14 moles of hydrochloric acid, and I put moles of barium hydroxide on the bottom, moles of hydrochloric on the, this is a 1 to 2, comes from my balanced equation. So basically I'm going to divide. That gives me my moles of my base. And then what I have to do is I have to divide by my, up here it says concentration. So I'm trying to find my volume. So I just take the moles I just found, divided by my concentration. This is in liters. So if I want to change it to milliliters, 1, 2, 3, be 41.4 milliliters. Okay, so when you're doing titrations, those are the steps. There's more problems on those and more steps and hints in the unit review notes. Okay. Here's another one. What do we got here? Oh, rice table. Okay. All right. So we got 1 mole of ammonium and 0.4 moles of Na are placed in a 5-liter vessel. So to find my concentration, you guys, I got to take my moles divided by my liters. 1 divided by 5. 0.4 divided by 5. That's how I get my concentration. If it doesn't list one and it's a product, it's 0. Okay, so my change in here, it says, is found to be 0.78 moles of NH3 present. Okay, so again, 0.78, that's what it says it has. That's the moles. I have to divide by my volume, 5. So this is my amount. Okay, so for my change, I take my amount that I have, 0.2, 0.155. So what I know is what it's at equilibrium and what it is initially. I subtract it to and I get 0.44. So on this one, this is a 2. So if I take this number times 3 and divide by 2, I get 0.066. On this one, I have to divide by 2. Because again, on all of these, I have to do mole ratios. And that's what I did up here. Okay, to show you what I did to get these numbers. So then you just add or subtract, and you've got what they are at equilibrium. So remember, equilibrium is products, concentration of the products over reactants. So I take this one times this one, and this one to the third power times this one. It's just, you know, to that power because there's no number, and this one to the second power. So I wrote those in there, and sorry, I covered up. It's 1.2 times 10 to the negative third. Okay, and again, it's just multiplying and dividing. Okay, looking at my time, I'm doing good. Okay, calculate the pH of a solution if it's made by a 0.1 molar pyrimidine and a 0.15 molar pyrimidine hydroxide. Again, we have the K sub A and the pH. Okay, so pH is the pKa. So what I'm going to do is I'm going to take this number and I'm going to take the log of it, and I get 5.25. And then here, log, I'm going to take the base, which it tells me up here, and the acid. So I just take the pH, again, it's just taking the log of this number. I take 0.1 divided by 0.15, and this is what this equals. So if I subtract it, I get 5.074. Now some of you might go, oh, is it this one first or that one first? If you divide them in the reverse order, you're just going to get positive. So look at your answer, okay? We're doing a pH of a solution. If we're adding a base to it, the pH is going to go up. If we're adding an acid to it, the pH is going to go down. In this case, we're adding an acid, so it's going to go down. Okay. Write the half reactions, oxidation and reduction. Okay, again, remember, oil rig, oxidation is loss of electrons. Reduction is gain of electrons. Okay, and again, it's a change in their oxidation numbers. The first thing to do, you guys, is look for ones that are all by themselves. This is not the case, but they have to change their oxidation number. And it's usually going to be the transition metals, manganese, and then carbon, sulfur, phosphorus, those guys. Don't look for like oxygen. Don't look for the alkali metals. Those guys aren't going to change unless they're by themselves. Okay. And here's another one. Again, I have sulfur by itself, so I know I got one. Okay. Sulfur goes from 0 to over here, it's +4. So I found one. The other one I have to figure out, and again, it's chromium. And again, it's just looking at the numbers. Okay. In this case, it goes from +6 to +3. So it has to be reduced because it becomes less positive. This one goes from 0 to +4. It's oxidized. Okay. So if it becomes more positive, it's oxidized. If it becomes more negative, it's reduced. Okay. Here's alpha decay. Remember, when you do alpha decay, I wish I could write it like they can, but it's 4/2. So basically, you take 241 minus 4, and you get 237. 95 minus 2, you get 93. And then you find the new element that's atomic number is 93. That's all you have to do. Okay, same thing here. 22 minus 4 is, 222, sorry, minus 4 is 218. 86 minus 2 is 84, and then I go find what element is 84, and that's polonium. Okay. Here's beta decay. It's kind of the same thing. 14, it's a 0, so it's still 14, but 6 minus 1, well, you're adding an electron, so it's going to be 7. So you add that on. Okay, so 6 is 7, and again, go find what element is 7. Potassium, the top number stays the same. add one to the bottom.